When working with the definite integral previously, it's been all about a single function and the area between that function and the x-axis. What we're doing in this video is instead of using the x-axis, we're going to use another function. So what we can do is find the area between two functions. When we evaluate this, we're going to be looking at a specific interval, and there's a few different ways that interval can show up, so we'll talk about those in the examples. But when we look at this interval, something we're going to want to evaluate is which function is larger than the other. So like which one's higher up on the y-axis and lower on the y-axis. So with that, if we have these two functions, so we're going to call it f and g, and we're looking on the interval from a to b. And let's say for this example that g of x is smaller than f of x. So in terms of appearance on the graph, is that f of x is higher up than g of x. Or you could say like f of x is our top function, and then g of x would be the bottom function. So if we want to find that area, what we do is we take our definite integral starting at a, ending at b, and we take f of x minus g of x, where f of x is that top function and g of x is the bottom function. So let's look at some examples and apply that rule. So this first scenario here, we're going to find the area that's bounded between the graphs f of x equals x and g of x equals 3 from x equals 1 to x equals 4. So some nice little functions here to work with. And in fact, we'll be able to do this one without calculus, but I kind of want to compare and contrast the two scenarios here. So f of x equals x, that's just our diagonal line through the origin with a slope of 1. So I'm just going to graph that over here. And then g of x equals 3 is just a horizontal line at y equals 3. So I have my horizontal line. And what you can see here is the two functions intersect at x equals 3. So to the left of x equals 3, we're seeing the g of x equals 3 is the top function and f of x equals x is the bottom function. So that 3 is higher up than x. And then as we go to the right of that intersection point at 3, we're seeing f of x becomes the top function and g of x is the bottom function. So it switches behavior across the intersection points. So we want to find the area from x equals 1 to x equals 4. So what I'm going to do is draw a vertical line at x equals 1, a vertical line at x equals 4. And in those areas, I want to find the area that's bounded between the two functions. So what we end up with here are two little triangles. We have the one that's formed between 1 and 3. So we have this behavior that's occurring from 1 to 3. And then 3 to 4, we have this little triangle here, and it's just switching because of how the behavior switches across the intersection point at x equals 3. So just using geometry here, or even just kind of counting, what we can see is this area, we have one block, a half, and a half, so 2.5 square units. So just kind of counting or thinking of the area of triangles, we can see we have an area of 2.5 here. But even though this process will take so much longer, let's look at the calculus of it, because then we'll need calculus for when we get to more complicated functions where we can't just use geometry. So if there's curvature to our graph, which we're going to see in the next 3 examples, we're going to have to use calculus, but let's just kind of see how it works together. Now, in terms of top function and bottom function, like I was saying, it switches across x equals 3. So what we're going to need to do is we're actually going to have two integrals. So the first integral, I'll have the definite integral from 1 to 3. And with this one, so again, I want to take that top function minus the bottom function. So from 1 to 3, g of x equals 3 is our top function. So I'm going to take 3 minus f of x, which is the bottom function of x, dx. And then we're going to be adding on from 3 to 4. And in that little triangle there, f of x equals x is the top function, so I'd be taking x minus, and then the bottom function would be the 3, and then dx. So 2 integrals to evaluate here. So from 1 to 3, the antiderivative of 3 minus x, so we're going to have a 3x minus x squared over 2 from 1 to 3, and then plus the antiderivative of x minus 3, so x squared over 2 minus 3x from 3 to 4. Okay, so we're going to plug in 3 first with the 3x minus x squared over 2. So let's see, 3 times 3 is 9, minus 3 squared, so 9 halves. I'm going to go ahead and change that to a decimal of 4.5. So there's plugging in 3, and then for our definite integral, we want to subtract plugging in the lower bound value, so the 1, so 3 times 1 minus 1 half. All right, and then I'm going to go plus, plugging in 4, so 4 squared, 16 divided by 2 is 8, minus 3 times 4 is 12. And then we'll have minus, plugging in the lower value of 3 squared over 2, so 9 halves, so 4.5, minus 3 times 3, which is 9. All right, so let's see, 9 minus 4.5 is just a 4.5, minus 3 minus 0.5, so 2.5, plus 8 minus 12 is a negative 4, so we have a minus 4. And then minus 4.5 minus 9, so a negative 4.5, so minus a negative 4.5, so plus 4.5. Oh, and how's that looking? Let's see, 4.5 minus 4 is a 0.5. Oh, let's just go with a calculator. And really with these, like, we want to see the process and like the plugging in, but from here, even if you just throw it in the calculator at that stage, completely fine. This is a 2.5, which completely matches with what we saw geometrically. So this one was special because we had to do 2 separate integrals because of the change of behavior. If the behavior stays the same in terms of what function is larger and which function's smaller, then you can just do 1 integral. But because of the change of behavior within the interval that we wanted to look at, we had to do 2 separate and add them together. All right, let's look at some more complicated scenarios. So we want to find the area bounded by the 2 functions f of x equals 3 minus x squared and g of x equals x plus 1. Now with this one, I can make a sketch of this based on my knowledge of graphing these types of functions. We have a parabola and we have a line. So that I could just make a sketch. If you're unsure about the sketch, you can always go to Desmos. I'm going to show you more with Desmos in the next example where it gets quite a bit more complicated. Like with this one, what I'll do is I'll make a sketch here. So 3 minus x squared, this is a parabola that's opening downward because of a negative x squared, and then it has a y-intercept, or the vertex is up at 3. So with that, I have an idea of what this will look like. So up at 3, I have the vertex, and then it's a parabola opening downward. And then g of x equals x plus 1, that has a y-intercept at positive 1, so maybe about there, and then a slope of positive 1, so something like this. So just with that information, I didn't get super specific here. I just need a sketch so I have an idea of what the area is going to look like. Because with this scenario, they didn't give us a range of values to look at for x. They just said, find the area bounded by the 2 functions. So with our picture here, with this parabola that opens downward, and then this line that's going through it, that top section with our vertex is being bounded by the line. So we end up with this kind of wedge shape that's stuck between the 2 functions. So what we want to do is we want to find that area in there. So what we need to do as part of the process for this is to figure out where this interval begins and ends. And where that's occurring are the intersection points. So our first step here is going to be to find the intersection points. So we can do that algebraically. We could also use Desmos, but I'll show that in the next example, but we can find it algebraically with this one. So we want to see where are these two functions equal to each other. So 3 minus x squared equals x plus 1. And we want 0 on one side, so that'll be x squared plus x. And let's see, 1 minus 3, so negative 2. So 0 equals x plus 2 times x minus 1 as we factor it. So that means we're getting an x equals negative 2 and an x equals 1. So that tells me where these intersection points are occurring. The smaller one is at x equals negative 2, larger one at x equals positive 1. So what that will do is that'll give us the beginning and end for our definite integral. And we don't need to worry about splitting up our integral because across this entire interval, 3 minus x squared is the top function, x plus 1 the bottom function. So to find the area bounded between the two, we're going to take the definite integral from negative 2 to 1, and then top function of 3 minus x squared, and then we're going to subtract x plus 1, so I'll have a minus x minus 1, subtracting that entire function. Make sure you have the negative distribute through. And then just to simplify it, so negative 2 to 1 of negative x squared minus x plus 2 dx. Then we'll take the antiderivative, so negative x cubed over 3 minus x squared over 2 plus 2x. And then we're going to evaluate from negative 2 to positive 1. So plugging in 1, we'll have negative 1/3 minus 1/2 plus 2. And then minus, plugging in negative 2, so at a 8/3 minus 4 over 2, so 2 minus 4. And we could just throw that into a calculator. In fact, let's do that together. So, because what we could do is, if you need the fraction answer versus a rounded answer, the Desmos calculator can help with that. But I'm just going to type this in parentheses, negative 1/3 minus 1/2 plus 2 minus 8/3 minus 2 minus 4, using my parentheses, and we're getting a 4.5 out. So when you plug into the scientific calculator, it'll give you a rounded decimal. I mean, this isn't rounded, 4.5 is exact, but you can convert to a fraction to see 9/2 if you need that fraction form, but decimal form is perfect too. So 4.5 for our answer. And what we could do is we could graph this and see if it does look like there are roughly 4.5 units bounded between those. That sounds pretty good to me. Okay, so let's look at another one that's harder to just make a sketch of. So f of x is 3x cubed minus x squared minus 10x plus 2. So I know that's cubic, so I have a general idea of what it might look like, but this is a tough one. So what I'm going to do is I'm going to show you how to use Desmos as support for this. So what I'm going to do is graph the two functions. So let's see here. 3x cubed minus x squared minus 10x plus 2. So there we can see we have a cubic function. It goes increasing, turns to decrease, turns to increase off to infinity. And then we have negative x squared plus 2x plus 2. So we have this parabola that's intersecting. So with the cubic and the parabola and how they're working together here. So I have my cubic that goes up, down, up. And then the parabola, which opens downward, so it goes up to the peak and then down. What we have are two regions here. We have this region where the cubic is the top function and the parabola is the bottom function. And then after that intersection, it changes behavior. So to find the area that's bounded between the two, we're going to have two areas to find in this. So that's where we're going to see the switch of which is the top function, which is the bottom function. What we're going to need is 3 intersection points. We have the beginning and end for that first section, beginning and end for that second section. So we could calculate those like we did in that last scenario of factoring and solving. If we've already graphed it in Desmos though, Desmos likes to highlight the intersection points of graphs. So what we could do is we could just grab the numbers here. So -2, 0, and +2 are the 3 intersection points. And all we really need is the x values. So x equals -2, x equals 0, x equals 2. So what we'll have here is the definite integral from -2 to 0, and that's where the cubic is the top function. So we're taking 3x cubed minus x squared minus 10x plus 2, and then we're subtracting the bottom function, which is the parabola. And what I'm going to do is subtracting this function, it's just going to change all the signs. So where we have -x squared, now we're going to have +x squared. Minus 2x minus 2. So that's the first region. And then we're going to add the definite integral from 0 to 2, where the parabola is the top function. So we'll have -x squared plus 2x plus 2 minus, and we're going to subtract the cubic function. So again, I'm just switching the sign of all the pieces. So minus 3x cubed plus x squared plus 10x minus 2 dx. All right, let's simplify these. So -2 to 0, we have a 3x cubed. X squared cancels out, so we won't have x squared. We have a -10x minus 2x, so a -12x. And then plus 2 minus 2 cancels out, so that's just a 3x cubed minus 12x. And then we're adding the antiderivative from 0 to 2 of, let's see, -3x cubed. X squareds cancel out. We have positive 2x plus 10x, so positive 12x. And then positive 2 minus 2 cancels out. So -3x cubed plus 12x. All right, taking the antiderivative, 3x to the 4th over 4 minus 12x squared over 2, so 6x squared. And we're evaluating that from -2 to 0. Then we're going to go plus and -3x to the 4th over 4 plus 12x squared over 2, 6x squared, from 0 to 2. All right, plugging in 0 is just going to be a big 0. And then we're going to go minus, plug in -2. Let's see here. 2 to the 4th is 16 times 3 divided by 4 is 12. Minus 6 times 4, it's 24. Then we're going to go plus, plugging in positive 2, so we're going to have a -3 times 2 to the 4th divided by 4. So that's a -12 plus 6 times 4, so plus 24. And then minus plugging in 0, which is a big 0. Okay, so let's see, this is going to be a -12, so that's a positive 12 plus a positive 12. So we're getting a 24 out. And because we ended up with 12 plus 12, that's telling me that the two areas are actually equal to each other, which, looking at this, does look pretty even in terms of the area bounded between the two regions on the graph itself. So that can help as a confirmation. All right. Okay, one more example here. I know it's a long video, but it's nice to see the different scenarios with these. So this one, the area of the region enclosed by x squared minus 6 and negative x minus 4. Now this is just a parabola and a line. So this, I'm just going to make a sketch myself. So x squared minus 6 is going to be a parabola that's opening upward that has a vertex at 0, negative 6. So we're going to have a parabola opening upward that hits pretty low on the y-axis for the vertex. All right, then y equals negative x minus 4 is linear, and that goes through negative 4, so a little above that vertex, and the slope is a negative 1. So with the line, it's this area that's bound between the two is stuck between the parabola and the line, where the line's on top and parabola is on the bottom. So we're going to need the intersection points. Now we could use Desmos to find them, or we could do it algebraically. This isn't too bad to do algebraically quickly. So x squared minus 6 equals negative x minus 4. So that's an x squared plus x minus 2, actually the same as up above that we did for factoring. So x plus 2, x minus 1. So x is going to be negative 2, x is going to be positive 1. So we're going to want our definite integral to go from negative 2 to positive 1. The linear function's the top function, so we'll have negative x minus 4, and then minus the parabola, the quadratic function, so minus x squared plus 6 dx. And let's see if we can simplify that a bit. So negative x squared minus x plus 2 dx. So we're going to have a negative x cubed over 3 minus x squared over 2 plus 2x from negative 2 to positive 1. Sorry, I'm just having flashbacks to that previous example, and I think there is some symmetry here in terms of the areas we're going to get out. Okay, so plugging in positive 1, so we'll have negative 1/3 minus 1/2 plus 2, and then subtract if we plug in negative 2, so we'll have an 8/3 minus 4/2 minus 4. That's the same as we did up above. This is going to be an area of 4.5. So even though this parabola and intersection with this line are occurring elsewhere, the shape is the same in terms of how they're intersecting with each other as that previous example that we had with the parabola and line. Because it's this nice slope of 1, and we're not doing any vertical or horizontal transformations to the parabola, it's kind of holding that shape. It's just occurring in a different region. And something to note too is when we're finding the area between two graphs, it's going to come out to be positive. So just because this one's occurring below the x-axis, is not going to show up as negative or positive. That's just when we're working with the x-axis. With these, you should always be getting positive answers out.